Let's look at the sample test 2 for Physics 244. So, first problem. So on the actual test there'll be a few multiple choice kind of conceptual things and some conceptual things before the problems, but that was on the other exercise that we have there. So we'll do that as a separate thing. So just looking at the problems here, consider parallel conducting plates as shown separated by 2 centimeters. So we got a distance here of 0.02 meters. Between the plates, the electric field has a strength of, this is our electric field, it has a strength of 400 newtons per coulomb. So E is 400, let's say it's going down, negative J hat newtons per coulomb. If we need that, we probably don't need the, we'll probably just use magnitude only here. We got a 0.2 gram, we got a mass here, 0.2 grams, so 0.0002 kilograms, and it has a charge of -1 nanocoulomb near the bottom plate, basically touching the bottom plate, and the bottom plate has a potential of 2 volts. Okay, what is the potential at the upper plate? Alright, so we've got a uniform field, we've got the equation delta V is E times D for a uniform field, and so we've got E, we'll just go magnitude wise here, so E is 400 newtons per coulomb, and we've got D, remember actually we can, maybe the better units for E in this case will be volts per meter. Remember we had alternate units for electric field is volts per meter, makes more sense here, and we got 0.02 meters, right, because we're wanting volts here, so we get delta V is, come on calculator, 400 times 0.02, pretty much 8. Okay, so delta V is 8 volts, and so so we got 2. Are we going to go down 8 to go to the positive plate from the negative plate, or are we going to go up 8? Well, when we go against the field, we get more energy, we get more potential, and so the voltage has to go up. And so the voltage up here has to be 10 volts because the change is 8. Delta V is 8, and so this one must be 10. So V at the upper is 10 volts. That's equals. Okay. Next part, what is the potential energy of the particle near the negative plate? So where it is here, right basically at the negative plate, we can say that its potential is 2 volts, and so we have potential energy is charge times potential. Yep, we may have the equation the opposite way on your equation sheet. Potential is potential energy divided by charge. Either way, you rearrange it, and you get what you need here. And so the charge is -1 nanocoulombs, 10 to the -9 coulombs. The voltage is 2 volts down there. And so potential energy is pretty much -2 nanojoules. Right, and potential energy can be negative, just below the threshold or whatever, below wherever we set 0. It's kind of, we had a similar kind of thing when we were talking about gravity, so that's okay. If the particle is released from rest, what will its velocity be as it passes the upper plate? So, sounds like an energy kind of a thing, right? We've got potential energy, we've got velocities, makes us think of kinetic energy, hopefully. So, we have only electric forces involved here. We're not worrying about gravity or loss, friction, or anything like that. So we'll have conservation of mechanical energy. So we can say PE1 plus KE1 is PE2 plus KE2. Okay, so we'll call this condition 1, and then right here when it's coming through the plate, condition 2. Alright, so first off, I guess I'm assuming that it's going to go that way, the way the arrow shows. Is that right? Well, yes, because it's a negative charge by a negative plate. It's going to be repelled. It's going to be pushed straight out there. Okay, so, but it says we're starting from rest and letting it go. So we can say that KE1 has V equals 0, so KE1 is 0. Right? KE2 is going to help us get the velocity we need, 1/2 mv squared. All right, how about the potential energies? Well, we got one of the potential energies here near the negative plate. We can call that PE1 because that's where it starts out, right? So PE1 is -2 nanojoules. I'll just write that in there, I guess. -2 nanojoules plus 0 equals PE2. PE2, let's just go ahead and calculate to the side here. Same exact process as Q times V2, V upper. Alright, and so that is the -1 nano, -1 10 to the -9 coulombs times the 10 volts now. And so we get -10 nanojoules. So -10 nanojoules plus 1/2 m is 0.2 grams, 0.002 3 zeros, 2 kilograms V squared. Right, so add 10 nanojoules to both sides, we're going to get 8 nanojoules equals 1/2 0.0002 V squared. Let's just solve for V here. So V is going to be square root of 8 10 to -9 joules divided by 0.0002. Taking care of the half brings a 2 up here. Multiply by 2 on both sides, cancel out the half, yes. And so we get our velocity is square root of 8 times 10 to the -9 times 2 divided by 0.3 zeros and a 2. It's like 8.94 into the -3. This is velocity. All of our units were standard units, kilograms, joules. Yes. So it's going to be meters per second. Excuse me. All right. Part D. If the -1 nanocoulomb charge is replaced with a positive 1 nanocoulomb charge, what would change in Part C? Well, the positive charge would be attracted to the plate, and it's already there, so it would hit the plate. The particle would hit the plate, or basically it's at the plate already. It would hit plate, stay there, right? It won't be repelled. It won't go anywhere. All right. That's good for number 1. Let's look at number 2. Consider a 20 nanocoulomb charge located at a point 0.05 centimeters in the 0,5 centimeters in the xy plane, and a -10 nanocoulomb charge located at 3,4 in the same system. What is the potential at the origin from these charges? Let's go ahead and get a little picture going here. So X and Y, we'll say this is 5 centimeters. And so we've got Q1, we'll call it Q1 is 20 nanocoulombs right there. And then we've got 3, that's 4, is about 3, something like that. 3 and 4. X is 3, yes. And then so Q2, -10 nanocoulombs. And it's about there. All right. And we're asked about what is the potential at the origin from these charges. All right. So potential is V, special V. Anyway, it's going to be V1 plus V2, potential 1 plus potential 2, and it's going to be potential for a point charge is just KQ over R, so it's KQ1 over R1 plus KQ2 over R2. In this case, we got a 3, 4, 5 triangle, right? So this one is going to be 5 centimeters as well. Or both of the R. This one is 5 centimeters for R. This is R1. and then this one, even though it might not look like it, they're both the same, R2. All right, so we've got K. K is our Coulomb constant, 8.99 10 to the 9th. And then let's just kind of factor out a little bit. Q1 is 20 nanocoulombs over R1, 0.05 meters. And then let's put the minus sign in there for the minus sign on Q2, negative 10 times 10 to the negative 9 coulombs, and then again 0.05 meters. Let's plug all that in. Oh, forgot my negative sign. Let's do a little editing here. Alright, don't forget the negative on the 10 here. Looks like the potential at 0, 0 is 1798 volts, or V00 is 1800 volts to 3 sig figs. Okay, what is the potential at the point negative 1, negative 1? Alright, so we want the potential now down here. Let's call that point A, it says. Alright, this is A is negative 1, negative 1. What is the potential down there? Alright, so this one is 0, 0. We'll just call this VA. Again, it's going to be the potential from 1 at A plus the potential from 2 at A. Alright, which is still KQ1 over R1A. Anyway, kind of funny naming, but we'll just go with it. R2A, just to distinguish between this R1 was to the origin. Now we're going to have new R1. It's going to be going over here. This is R1A, and then this one. Anyway, R2A. Alright, going to the distance to this point, to point A from the original two charges. Alright, so we got our K pulled out, so we can pull it out again, 8.99, 10 to the 9th. And Q's are the same, 20 times 10 to the negative 9, and negative 10 times 10 to the negative 9. But now the R's, so let's, okay, so R1A, it's 5, well, all the way down in the Y direction, the difference is 6, because it's 5 and then one more, so it's going to be the square root. This side is 6, this side is 1, so square root of 6 squared plus 1 squared, keeping things in centimeters for a moment. So R1A is square root of 6 squared plus 1 squared. Anyway, square root of 37 pretty much. 6.083 centimeters. Similarly, R2A, again, now we're going to have this triangle, so now one side is 4 and then this side will be 5. We'll do the square root of 4 squared plus 5 squared. .403 centimeters. Alright, so down here we need meters. So let's put in for R1A 0.06083, and this one will be 0.06403. Alright, so V at A, plugging all this in, 8.99, 10 to the 9th, times, in parentheses, 20 times 10 to the negative 9 divided by this 0.06083 plus, or not plus, let's do it right this time, minus 10 times 10 to the negative 9 divided by the new R2, 0.0604, no, 0.06403. Okay, and so this new V comes out to 1552 volts. Let's round. VA is 1550 volts. Potential at point A from those two charges. Alright. It's a bit farther away from both of them, so it has a weaker effect from both of them. Seems to make sense. Alright, sketch the forces from each charge and the total force at that a 5 nanocoulomb charge would feel if it placed at point A. I'm just going to redraw point A down here just for now. And so the first, so Q1 is up here. Let's just say Q1 is up here, and then Q2 is over here. So relatively, Q1 is a positive charge. Test charges are always positive, so it's going to be pushed away, something like this for F1. Q2 is negative though, so it's going to be attracted. We're just trying to get a general idea here. We'll do our parallelogram, and so our total F, we would expect something like this. So it doesn't ask us to calculate it, it just says sketch the diagram, but we're expecting a force, you know, somewhere, something like down here, something for our total force from those two. But it didn't ask us to calculate, but it just asked for the sketch. Just remembering last chapter. Okay, how much work would an external force need to do to move a 5 nanocoulomb charge from point A to the origin? So we're going to start at A, and we're going to go to the origin. It doesn't want to go there naturally, so we're going to have to do some work on it. We expect some positive work needed because it's trying to go the other side. It's not if the force is pointing straight at it, the field would do all the work, and we would kind of basically have to hold it back from going too fast. But it's not going that way, so we expect to be positive work. But anyway, so the work applied is going to be negative, or is going to be actually the change in potential energy. The work of the field is negative the change in potential energy, but the work applied is equal to the change in potential energy. If we, just like the eraser, if we lift the eraser up, we are doing work and we're giving it potential energy. Alright, so that's what we're doing here. We're pushing it closer to the origin, which means it's going to have more potential energy, so we have to do work. Good. Okay, so delta PE though is Q times delta V, where V is the potential. And so we've got a 5 nanocoulomb charge, and our change in potential is final minus initial. Final is 15, we'll go with extra sig figs, 1550, no, the final is at the origin. We're going from A to the origin, so that's the 1798 minus the 1552. Those are volts. So our work applied, 5 times 10 to the negative 9 times 1798 minus 1552. 1.23 times 10 to the negative 6 joules. 1.23 microjoules. Yep, looks like I agree with what I did earlier, so hopefully those are the right numbers. Alright, next problem. Consider the capacitor circuit shown. We have, hopefully that's readable there, 5 microcoulomb, or microfarad capacitor, and then that is in series with this whole bunch that are in parallel. a 2, a 3, and a 4 all in parallel with each other, right? And so it says, what is the equivalent capacitance of this circuit? So let's go ahead and draw an intermediate circuit just so we can remember. So looking at the circuit, hopefully it's obvious that these are all in parallel. If we make those into one equivalent, so the source will stay the same, the 5 microfarad capacitor stays the same, but now we're going to have some sort of C equivalent 1 here, which is going to be 3 capacitors in parallel. These 3 are going to be mushed into one C equivalent to start with. And when we combine capacitors in parallel, how do we do it? We just add them up. So it's just going to be 2 microfarads plus 3 microfarads plus 4 microfarads, right? Because series caps add up. Alright, so C equivalent 1 is 3 plus 2 plus 3 is 5 plus 4 is 9 microfarads. Alright, now we've got 2 capacitors in series, a 5 and a 9. So combined in series, if we do that, then we'll just have 1 capacitor left, right? We still have the same 10 volt source. It doesn't know anything's happening here. But now we're going to have C, let's just call this one C total, just to call it something different. And it's going to be for C total is 5 microfarads in parallel with 9 microfarads, which is going to be the 1 over 1 over stuff. So 1 over 5 plus 1 over 9. If we leave everything in microfarads, we're okay to do this as 1 over 5, 1 over 9, kind of whole number things. And so we're going to get C total is 1 divided by 1 divided by 5 plus 1 divided by 9. 3.214 C total 3.21. Don't forget the microfarads. Alright, so it kind of got out of hand here, but 3.21 microfarads is the total equivalent capacitance of the circuit. What is the charge stored in the entire array of capacitors? So this C total is representing the total array, the total bunch of capacitors put together. And so if we find the charge out of the battery, which will be the charge of the total of the whole array, we can just do that. So Q, I guess we'll just call it Q battery equals Q total. We can do QVC with the C total, so V total, C total. Alright, V total is the voltage of the whole thing is just the source voltage, so that's the 10 volts. And then C total we just had there, 3.214 microfarads. So Q total is 32.14 or 32. And we'll keep 14 microcoulombs. Officially, Q total 32.1 microcoulombs to round here. Alright, draw equivalent circuit with the array reduced to 1 capacitor, include known values. So basically just wanting you to remember, I kind of have it up there already, 10 volts, and this one is the 3.21 microfarads, and the Q is 32.1 microcoulombs. Something like that. If you had, especially if you hadn't drawn it already, we'd want you to have it there. Alright. Part D. Find the charge, voltage, and potential energy for each capacitor to fill in the table. So we want to basically solve the whole circuit, write in find the voltage, the charge, and then calculate the potential energy for both of them. So for the capacitors, if we could find the voltage and charge, that kind of defines the whole voltage and charge for every capacitor. We've solved the whole circuit, basically. Alright, so let's start with this information we have here, we've got Q of the equivalent circuit, all right, which is Q of the battery, and let's take a step back actually and look at this equivalent circuit that has 2. Because we can get our 5 microfarad capacitor back, let's go ahead and call this V5. Let's just call the voltage between these, I don't know, VC or something for the combination there. And so V5 is here. V5 is the voltage across the 5 microfarads, and VC would be here in this circuit, because this is representing the parallel combination, and this is the parallel combination. They both have the same voltage, so this is VC. A little hard to read there. Minus sign VC. All right, so looking at this circuit now, let's see. If we knew V5, we'd get VC, but we haven't. Let's work on the 5 microfarad capacitor first. So, can we get V5? Yes, we can do QVC, Q5 equals V5, C5, and then we can rearrange, so V5 is Q5 over C5. What is Q5? Well, it's in series with the battery. The battery has this total Q, right? So the things in series, C equivalent 1 and the 5 micro both have to have that same equivalent Q. So Q5 is Q battery, right? And so we've got 32.14 microcoulombs over C5, which is 5 microfarads. The micros cancel basically. And so V5 is 32.14 divided by 5. 6.428 volts. But let's, in the table, we'll just keep 6.43 volts. Alrighty. Just double check my work here a second. So far, so good. And the charge, we already said the charge was the charge of the battery. That's the 32.1 microcoulombs. Alrighty. We can calculate the potential energy, I guess. Potential energy 5. Let's use the 1/2 CV squared version. So C5 V5. So that's 1/2 C is 5 10 to the negative 6, and voltage is that 6.428. And so let's do that 0.5 times 5 times 10 to the negative 6 times 6.428 squared, 103 microjoules. Alrighty, so that's good. Now we've got the 5 microfarad capacitor figured out. Now let's go back to this circuit and we can use that to get VC. So let's just do KVL on, if we call this circuit 1, this circuit 2, this circuit 3. So KVL on circuit 2, just go around the loop here, so we get negative 10 going through the source. Hit the negative side first, negative 10 plus V5 plus VC, got back to the same point, equals 0. And so this tells us then that VC is 10 minus V5, and V5 is 6.428. So VC is 3.572 volts. So VC, excuse me, need to sneeze. Okay, VC is 3.572 volts. So is VC, help us get anything in this table? Is VC the voltage on any of these capacitors? Well, VC is the voltage across the parallel combination, And so let's go back to circuit 1. VC is across the parallel combination. It has the same voltage as, that's what parallel things have, is they all share the same voltage. So basically V2, V3, V4 are all VC, right? They're in parallel and they all have that VC voltage. So all three of these capacitors have that same voltage, so we can put 3.57 for all of those, because they're in parallel and they have that VC voltage. Good. Now we need charges, so let's go QVC. Q4 equals V4C4, but V4 is VC, VCC4. Alright, so we got 3.572 volts times Q4 is the 4 times 10 to the negative 6 farads. And so Q4 is 3.572 times 4 times 10 to the negative 6, 14.29 microcoulombs. Do 14.3 microcoulombs. Similar process for the next ones. Q3 is again VC3, VCC3, and 3.572 times 3 times 10 to the negative 6 farads. .7 microcoulombs. And then Q2, same thing, VCC2. .14 microcoulombs. Alrighty. So, running out of space here. Potential energy, this is a little bit repetitive here, but we'll go ahead and do it. So, potential energy 2, 1/2 C2 V2 VC squared. 2 times 10 to the negative 6 times 3.572 squared. Yes. 12.8 microjoules. Oops, that was 2. Same thing for the other two. P3, 1/2, 3 times 10 to the negative 6 farads times the 3.572 squared volts. .1 microjoules. And PE4. Something. I got a different number for the 3. Let's double check that one. This time I get 19.1. I don't know what happened. 19.1. is what I got last time, so let's go with that. Alright, last part here says, what does the total charge of the parallel combination match the charge of the 5 microfarad capacitor, and should it? Alright, so the total charge of the combination, so these three added together, should they be equal to the charge of this? Yes, they should, because they are in series, right? So the total charge of the battery comes here, and then it's going to come here, and it's going to split. Some of it's going to go to that one, some of it's going to go to here, some's going to go to the 4 microfarad. So some to the 2, some to the 3, some to the 4. But the total that comes can't go anywhere else, has to go to those 3. So the total that was in 5 should add up to be what was in the other 3. So let's just try Q2 plus Q3 plus Q4. What is that? We get 14.3 plus 10.7 plus 7.14 is 32.14 microcoulombs. And is it equal to Q5, 32.1 microcoulombs? So yes, they are equal and should be equal. Right, because they are in series. The parallel combination and Q5 are in series. So they should have the same charge. Alright. Next page. Calculator is escaping here. Resistor circuit. We've got one battery, a bunch of resistors. Draw a sequence of 3 reduced size circuits that are equivalent to the original circuit. Make the last circuit contain only one resistor. Okay, so looking at the circuit, trying to find things that are in parallel and series, hopefully we notice that these two are in series directly and these two are in series directly. If we combine two resistors in series, we get an equivalent. We'll call this R left is going to be what? It's going to be R2 plus R3, right? When resistors are in series, they just add, so it's going to be 4 plus 8 ohms, right? Whereas R right is going to be, again, R4 plus R5 is 10 plus 4 ohms. All right, so if we redraw the circuit, so if this is circuit 1, circuit 2, maybe we're going to do 3 more, so we'll get to 4, but circuit 2, we'll keep the source, 5-volt source, and this 4 ohm resistor here, but then we're going to have 2 this combination becomes 1 resistor, and the other outside one becomes 1 resistor, so this one will be a 12 ohm resistor, and then the outside one becomes a 14 ohm resistor. Alright, so there's our equivalent circuit. Now hopefully we can see that these two are in parallel with each other. So if we do the next circuit, we'll keep the 4 ohm resistor there, but now we're going to combine those two in parallel. And this R equivalent is going to be 12 in parallel with 14, which is 1 over 12 plus 1 over 14. So this R equivalent is 1 divided by 14. 6.462 ohms. Alright, so that's circuit 3. Circuit 4. Is the last circuit should contain only 1 resistor, and that's what we've gotten down to, because now we got these two in series. Resistors in series add, let's call it R total, is going to be R1 plus R equivalent is going to be 4 plus 6.4, so 10.46 ohms is R total. This is still the 5-volt source. Okay. Find the equivalent resistance of the we just did that. The equivalent resistance of the combination of all the resistors. So we kind of did that as we went through the circuit. So we've got our total is 10.46 ohms. That's good. All right, now we got another handy dandy table here. We want to find the voltage, the current, and the power in all of our 5 resistors here. So and the source and the battery. All right, so let's go ahead and put a current in here, I1. If we're looking at our smallest circuit, that'd be the easiest one to solve stuff in. I1 is the current out of the source. We can put I1 will be the current here. I1 is always the current in the source. It's also the current in R1 in the 4 ohm resistor when that is in the circuit. Let's just call this V1. This is the voltage across R1. Let's name this V combo there. This is also V combo here. V combo would be the voltage all the way from top to bottom here, and it's also the voltage on this one as well, right? And we can call this V2. Let's just give everything names so we know what we're talking about when we write equations. Alright, so we've got I1. Let's just call this I2, and let's just call this one I4 since it's going through R4. So those currents don't show in this circuit because they're combined, but over here I2 is the current in this parallel combination, so it's got to be the I2 goes through the 12 and I4 goes through the 14. Okay, so we've kind of gone through our circuits and put in the voltages and currents that we're going to need to calculate all of those down here, looks like. Okay, so what can we solve for? Well, we want to start solving things. It's going to be hard to go to this circuit because we don't know too much about this circuit, but we've got a little circuit that we know a lot about, right? So we know the voltage across the battery, which will be the same as the voltage across the resistor because there's only 2 things here. And we know the resistance, so we can use Ohm's law here. V equals IR, and in this case we've got I1 and we've got R total and we've got V of the battery. V of the battery is V total, the voltage across the resistor. So we can get I1. So I1 is V battery over R total, 5 volts over 10.46 ohms. So I1 0.4780 amps. Alright, so we got something here. So I1 is 0.478 amps. Alright, how about V1? Well, V1's not in this circuit, but we can back up. So we can go over here. So I1 is the source current, same source is here, same current. And so now we can see that I1 is the current in R1, right? And so we can do Ohm's law for R1. Says V1 equals I1 R1. Yes. So V1 equals I1, which we just got 0.4780 amps, and then R1 is the 4 ohms. So we can get V1 is 0.4780 times 4, 1.912 volts. So V1 is 1.91 volts. So we're getting somewhere here. For this last column, we're going to use PIV. P equals IV. Just multiply those two together. 1.912. Whoops. 912 times 0.478 0.914 watts. All right, just double check a little bit of it stuff here. I guess if I kept more sig figs, it ends up being 0.943 or 913. Anyway, we'll go with 0.914. And all right, so we got V1. Let's see, can we get anything about R2? Well, we've got to, we don't really have information about R2 and R3 separately yet. If we had its current, we could go V equals IR to get its voltage. The current is over here. The voltage, V2, isn't in this circuit. But we can use, actually, let's take a step back to this circuit and get VC. And then once we get VC, we can use Ohm's law to get I2 and I4, and then we can go back here. So let's get VC. So let's do KVL for circuit 3. All right, and so start at this bottom corner here. We'll have negative 5 volts plus V1 plus VC. All right, coming into the pluses. We got walking around here. We walked all the way around. We got back to the start, and so it equals 0. All right, so that tells us VC is equal to 5 minus V1. 5 minus V1, 1.912. So VC equals 3.088. That's an 8. All right, so VC, though, isn't the voltage across any one resistor in the big circuit, but it's the voltage across both of these parallel branches. Excuse me. So let's go up to this circuit 2 now, and we can work on finding I2 and I4. So from circuit 2, if we look at the middle branch, Ohm's law, middle branch, circuit 2, we say VC, V equals IR, VC equals I2 times the 12 ohms, right? And so I2 then has to be VC over 12, and VC we just had, 3.088 volts, 12 ohms. I2 is 3.088 divided by 12, 0.2573 amps. Okay, so I2 is the current in some of our individual resistors. It's the current in R2 and it's the current in R3. They're in series. They have the same current. So we can fill in some numbers here. 0.257 amps. 0.257 amps for R2 and R3's current. Alrighty, that's good. Let's do a similar thing for Ohm's law on the outer branch of circuit 2. And so VC equals I4 times 14 ohms. Alright, because we got VC is the voltage from bottom here to top here, so VC is the voltage across the 14 ohm resistor. So VC then, V equals IR, VC equals I4 times the R, which is the 14 ohms. And so I4 is equal to 3.088 divided by 14. So I4 equals 0.088 divided by 14 this time, 0.2206. So now we've got, that's the current in both R4 and R5, so 0.221. Alright, we're getting somewhere. Let's see, battery, we got a lot of stuff for the battery. Battery voltage was given as 5 volts, and then the battery has I1 in it. We have I1, 0.478 amps. Alright, doing pretty well here. So we've got all the currents, so now it's easy to get the voltages just with Ohm's law. So for each individual, so we're back to the full circuit now, and we can say V2 equals I2 R2. Yes. And I2 is 0.2573 and R2 is 4 ohms. Amps times ohms gives us volts, 0.2573 times 4, 1.03 volts. V3 equals, what's the current in V3? I2. I2 R3, 0.2573. R3 though is 8. Should be double, 2.06 volts. Alright, V4. What's the current in V4? We called it I4. I4, R4. And notice the way I named everything, positive sign convention, the current goes into the pluses of everything, so everything is positive, so that's good. 2206 for the current, and R4 is our 10 ohm resistor. So pretty much 2.21 volts. And then finally V5 is the current in in R5 is I4 still. R5, 0.2206 times R5 is another 4 ohm resistor. .88. We'll just go with 0.88 volts. Okay, and let's just do PIV for everything, multiplying them all times voltage times current to get the power. 1.03 times 0.257, 0.265, 2.06 times 0.257, 0.529, 2.21 times 0.221, 0.488 watts, 0.88 times 0.221. Being a little sloppy with my sig figs here, but should be good. Alright, we got our table filled in. Now, how is the power produced by the battery related to the power absorbed by the resistors? Well, should be the same, right? The battery is supplying all the power to everything, so whatever comes out of the battery has to go somewhere, goes to each of the all the resistors combined. So we should have P of the battery equals P1 plus P2 plus P3 plus P4 plus P5. Alright, so let's just check. P1 plus P2 plus P3 plus P4 P5 equals what? Let's do this. 0.914 plus 0.265 plus 0.529 plus 0.488 plus 0.194 equals 2.39 watts, which does equal P battery. Yay! They match as they should. Alright. Kind of a conservation of energy thing. These are, power is the flow of energy. And so whatever's pumped in by the source is used up by the resistors. not use up, but converted to heat or whatever by the resistors. All right, that's good. Let's look at the back page here. The circuit's a little hard to see. We've got a voltage source, VS1, in series with a couple of resistors, RA and RB. And then we got a resistor in the center here, RC. And we got on the outside, we got two resistors in series with a voltage source, VS2, RD, RE. All right, voltage source, battery, same thing, right? All right, so part A, define and label each resistor with a voltage. Define and label. Anyway, defining and labeling a voltage for each resistor is what it means. We want to use the sign, the positive sign convention. So it actually is probably easier to go ahead and start with the currents so we can see what's going on. And so for a positive sign convention, out of a battery, out of a source, we expect the current to come out of the positive. So let's start with a source and say that's I1. I2 has to come out, but we kind of got it backed up a little bit. So we can draw it. There's only one current in this branch, only one current in this branch, and so I2 needs to go this way, right? It needs to go up because drawing it over here comes out of the plus then, right? Into the minus, out of the plus, same thing. So in this branch, I2 needs to be going up. Same thing here. And then thinking of the currents at this node, then if I2 is coming in, I1 is coming in, I3 must be going down in the center. All right, so that's kind of actually doing part B first, but that gives us a good sign convention for the currents because of the sources. The sources are the drivers, and so if we want to get everything positive, it's good to start with them. And now let's define the voltages on the resistors. For resistors, positive means positive happens when current comes into the plus. So we want the plus to be the side where the current's entering RA, for example. It's entering from the left, so that's going to be the plus. So I'll call that VA. Down here, I1 is actually going this way, right? Continuous. So I1 is going this way, so it's coming in the right-hand side. So let's put the plus there. Name VB that way. Right? VC, again, plus coming in, the I3 is coming down, so the plus is the top, comes in the top, goes out the bottom. Over here, I2, and draw I2 again over here. I2 is going this away, so to come in the plus on RE, it has to come, the plus has to be in the bottom. We'll call that VE. And then again here, same thing, come in the bottom. It's coming in the bottom, so the bottom needs to be the plus, so VD is like so. All right, so if we name it like that, we got nice positive sign convention. Our equations will make us happier when we write them. Okay. Part C, write a KVL equation for the loop on the left. So we've got a loop here. We're going to write KVL. KVL says add up the voltages going around a closed loop. They had to be equal to 0. The way we do it is we think about starting at a certain point and walking around. We're just walking around this loop. When we hit a negative sign first on a voltage, we write a negative sign in the equation. If we hit the positive side first, we write a positive sign on that term. So let's just start on this one. We're going to start here. We're going to go around. We're going to hit negative VS1 because we're coming the negative side first. Continue walking around. We're going to hit RA. We're going to hit its positive side first. We're going to have a plus VA. Adding up voltages. Coming around here, coming down here, we're going to hit the plus of VC first, so it's going to be a plus VC. Continuing on around our loop, we're going to hit the plus of VB. And we're coming over here, we've gotten back to where we started, so we say equals 0. We went around a whole loop, the voltages have to sum to be 0. We go up the elevator, down the stairs, back to where we started. We've got 0 difference. Remember, voltage is really potential difference. We've got 0 difference going around the loop. All right, let's do the right loop. Yes. Start at this center bottom part. So we're going to go up first. We're going to hit negative side of VC. We got negative VC. Continuing on to the right side of the loop, we're going to hit the plus of VS2. So we're going to say plus VS2. Next one is RD. We're going to hit its negative side, so it's negative VD. RE, again hitting the negative side, so negative VE, coming back to where we started, equals 0. Alright, write a KVL equation for loop made by the outsides of the circuit. So we're going to just go around the outside like this. Let's just start at this left-hand corner again. So we're going to have negative VS1 plus VA, moving on to the source, plus VS2, negative side of VD, negative side of VE, positive side of VB, and we're back to where we started, equals 0. Alrighty. Write a KCL equation at the top center node. So we want to write a KCL equation here. KCL says what? Kirchhoff's current law. Current in equals current out, or the sum of the currents equals 0 if you call one of them positive, one and in positive and out negative. But let's just do, I like in equals out. So what's coming in here? We got I1's coming in. Anything else coming in? Yes, I2 is coming in. Anything else coming in? No, I3 is going out. So in I1 plus I2 equals out I3. All right, we could write another equation down here. Let's just for practice write the KCL equation at the bottom node, bottom center node. What's coming in here? We've got I3 coming in. What's happening down here? Well, I2 is going all the way around, so I2 is actually going out of this node, and same thing for I1. This is I1 is going out, so there's nothing else coming in. Only I3 is coming in, and I1 and I2 are going out. All right, so this equation doesn't help us much. It's the same equation as we had here, and so it's not going to give us much help in trying to solve for stuff. But for practice, it's good to just double check ourselves. Okay, part G. Write Ohm's law for each of the resistors. Use RA equals 1, RB equals 2, RC equals 3, RD equals 4, RE equals 5 ohms. Okay, so Ohm's law, V equals IR. So VA equals IA RA. IA is I1 though, so V1 equals I1 times 1 ohm. So VA equals I. 1I. Alright. VB equals 1I1, I should say. VB, where's VB? Down here. So VB also has I1 and then RB, which is 2 ohms. And so we can say VB equals 2I1. Alright, we're kind of seeing the pattern here. VC is what's the current in VC? I3. And RC is 3 ohms, so we're going to say 3I3. So VC is 3, which is RC, times I3. VD, current in VD is I2, and RD is 4, so it's going to be 4I2. And then finally VE, its current is also I2, and its resistance is 5, so we're going to say 5I2 for VE. Okay. So now we've got the voltages written in terms of the currents. This is going to help us because when we get here, use Ohm's law and some of your KVL and KC equations to find the currents produced by each of the sources. Use VS1 is 10, VS2 equals 20, and then all those resistances we just said. So we've got some algebra to do here, but let's just start with this equation. And so VS1 is 10, so we're going to have negative 10 plus VA. VA is 1I1, so just I1 plus VC. I'm going to write it up here. VS1 plus VA plus VC plus VB equals 0. So VA is I1, 1I1. VB is 2I1. And I want VC actually. first, and then VB. VC is 3I3, and VB is 2I1 equals 0. Alright, so if we rearrange this, let's solve it for I1. So this is 3I1 is equal to 10 minus, so 10 minus 3I3 divided by 3. Maybe doing too much in my head here, but double check my work there, but I think that works. And let's try the second KVL equation here. So we're going to do negative VC plus VS1 or 2 minus VD minus VE equals 0. So negative VC is negative 3I3 plus VS2 is plus 20 volts minus VD is 4I2 and minus VE is 5I2 equals 0. So this says that, well, let's not do too much in my head. So we'll say 20 minus 3I3 equals 9I2. So I2 is equal to 20 minus 3I3 over 9. Alrighty. So we've got I1 and I2 solved in terms of I3, and then we can use this equation. So I1 is 10 minus 3I3 over 3 plus I2, which is 20 minus 3I3 over 9, has to be equal to I3 itself. So we got one equation and one unknown now. So we can solve for I3. Okay, so let's see, 10/3 minus I3 plus 20/9 minus 1/3 I3. Let's bring this I3 to this side, minus I3 equals 0. Alrighty, let's make this into ninths so we can add these. So we got 30/9 plus 20/9, so 50/9. And then the I3s, we got negative 2 and minus 1/3, so minus 2 and 1/3. I3 equals 0. Whew. Alrighty, we shouldn't be writing so big, I'm going to run out of room. So I3 is equal to, bring this to the other side, for example, we're going to have 50/9 divided by 2 1/3 is 7/3. Anyway, I think we need calculator help here. So I3 is 50 divided by 9, that whole thing, divided by 7 divided by 3. Is, well, I don't know, 50 over 21, which is 2.381 amps. But that doesn't answer the question, because we want the currents in the sources. So we want I1 is the current in VS1, so I1 is here, 10 minus 3I3 over 3 is 10 minus 3 times 50 over 21, divided by 3. What is that? 10 minus 3 times 50 divided by 21. All that divided by 3. 20 over 21. 0.952 amps equals I1. And then I2 is here, 20 minus 3 times I3, which is 2.381, all that divided by 9. I2 equals 20 minus 3 times 2.31, all of that divided by 9, 1.43 amps. See how I'm comparing to what I've got before. I1 2.38. No, I1 0.25. I2 2. Okay, or I3. I1 is 0.953. Yes. I3 1.43. Okay. I named them something different when I did it last time, but I think they agree. So we've got our two things here. This is the VS2 current, and this is the VS1 current. And that's what we're asked for. Find the currents by each of the sources. Good. Whew. Okay. And then, what is the voltage across RD? So we call that VD is what? Okay, so at this point we've got all the currents in the circuit. It should be pretty easy to get any voltage using Ohm's law. So we're going to use VD equals I that's in D, which is I2, times RD. And so I2 is 1.43, give or take a sig fig, and RD is 4 ohms. So VD equals 1.43 times 4, 5.72 volts. Let's see, something like that. I had 5.71 last time, but I might have rounded a little bit more this time than I did before. All right, so that gives us a good idea on how to solve a circuit. Use KVL, KCL, Ohm's law. I think that's good for that test.